Hi everyone, good morning. Okay, so let's get started. Okay, Ajay is saying that we need one probability quiz. Yes, Ajay, it is ready actually. So it will be uploaded today only. Okay, so don't worry, it is ready. So hello everyone. Good morning. Hello Sonam. Hello Mahesh. Hello Tarun. Okay, so let's get started with today's topic. So today we are going to see more examples or more questions on covariance. Okay, and then we are going to see covariance metrics, and then there is one more topic related to covariance, which is correlation. So we are going to see these three things. Okay, so let's get started. Now, let's just first start with more questions on covariance. Okay, let's solve more questions on covariance, and then we will be, understanding this covariance more just by solving more questions. So, if you remember, what was the covariance? Covariance was the expected value. Okay, or you can say you can write in this form, or you can say that expected value between x minus expectation of x into y minus expectation of y. Now, if you remember that here, this expectation x minus expectation of x and y minus expectation of y, this is the key term, right? This is the key term. So basically, depending on the signs of both of this, right? If both of them are positive, then the whole term is positive. If both of them are negative, then also whole term is positive, right? So depending on the sign, this term will take the sign. I mean, which means that if both of them are positive, then this term will be positive. Otherwise, if both of them are negative, then also it is positive. Otherwise, it is negative. For example, positive times positive and negative times negative is positive, right? Okay. Otherwise, this term is negative. Okay. So this term was main. Now, let's solve more questions. And here, just before solving the question, let me just remind you that what was the covariance. So basically, positive covariance means that x and y are typically big together or small together, which means they are varying together. Negative covariance means whenever x is big, y is small, and vice versa. Okay. And these are the few properties of covariance. Specifically, that if the covariance, if you are finding between x and x only, then it is a variance of x, and covariance of x and y, which means how bad or how good x grows with y, is same as how bad or good y grows with x. Okay, so covariance of x and y is same as y and x. It is very simple thing to prove. And then if you multiply by any constant, you can take this constant outside, and covariance of x comma y plus z is nothing but covariance of xy plus xz. And if you want to find out variance of x plus y, okay, so in general the formula is that variance of x plus variance of y plus 2 into covariance of x into y. Do you remember the expectation of x plus y? What was the formula? It is expectation of x plus expectation of y, right? So it is always true. But for the variance, if x and y are independent, then it is zero. Okay. Then this variance of x plus y equal to variance of x plus variance of y only. But in general, this is the formula. Okay. Are you getting my point? So what I'm saying here is that, see, what I'm saying, that this is a general formula. Okay. But if x and y are independent, then we have something like this. In that case, the covariance actually is zero. So that is why we will say it is the case. So here this will be actually 0. Okay. So this holds. Understood? Okay. So now let's just see more questions. So suppose they ask you to simplify these few expressions, which means covariance of 8x plus 3, comma 5 by minus 2. So how to simplify this? Let's just see. Okay. So covariance of 8x plus 3, comma 5 by minus 2. So first of all, tell me, can I write it like this? 8 into 5, covariance of x plus 3 by 8, something like this, right? Comma y minus 2 by 5. Let me know. Is this okay? Which means if there is one constant here, Let's just see this. If there is one constant, you can take this constant outside, right? If there are two constant, then there will be two constant. Understood? Okay. Now, what about covariance of x plus something? Does plus and minus matter in the covariance? So what do you think? Which means, can I say covariance of x plus a comma y is same as covariance of x y? Yes, right. I think this is one of the question we did in yesterday's class. So basically, just like variance, in case of variance also this plus and minus doesn't matter. In case of covariance also it doesn't matter. So basically, it is same as 8 into 5 covariance of x comma y. Okay, let's just see this. So this is same as 40 into covariance of x comma y, right? Similarly, you can just simplify these terms. Okay, this is easy to simplify. Okay, this is little tricky. So basically here they're asking this covariance. So plus two you can anyway remove. So you are left with this. Then 10. Okay, so what you can do, you can apply the formula here where this x and 10x covariance and x and minus 3y covariance, right? So minus 3 they have taken outside. So basically it will be 10 into variance of x minus 3 into covariance of x comma y. Okay, just using the properties you can easily simplify this, right? Okay. Now, let's just see this. Suppose x and y are the random variables on same probability space. If variance of x plus 2y equal to variance of x minus 2y, then are they uncorrelated? So, what is the definition of uncorrelated? It means basically they are asking that check the covariance between x and y. Is this zero? Okay. Is this zero? So, this is what they're asking. Is this zero? So, let's just see. Let's just see how to do this. And what is the next question? If variance of x and y both are equal, then can we say they are uncorrelated? So, for example, this is given, right? So if you expand this, this means this first term means variance of x plus 4 into. So basically, you can apply the formula here, right? This is the formula variance of a plus b. See here. So it is variance of x plus variance of y plus 2 into covariance of x plus y. So if you apply this formula here, what you will be getting? Let me go to the next page. Using this, right? Using this, what you will be getting? Variance of x plus variance of y, right? So variance of 2y plus 2 into, if you remember the formula, 2 into covariance of x comma y, right? So it is 2 into covariance of x comma 2y. Now, this is same as variance of x, obviously, plus, should I take 2 outside or 4 outside from the variance? From the variance, should I take 2 outside or 4 outside? What do you think? It will be 4 outside, yes. So it will be 2 square basically, which is 4 variance of y plus, and then this is 2, right? So tell me, should I take 2 outside or 4 outside from here, from the covariance? From the covariance, you need to take 2 outside, and 2 is already there, so it will be 4, right? Covariance of x comma y. Okay. And from here, you will be having, I think, the similar terms. So it will be variance of x, right? Minus, minus, sorry, or maybe you can say plus basically variance of minus 2y, right? Let's just write this way, plus 2 into covariance of x comma minus 2y. Okay. So which is same as variance of x plus, basically minus 2 square will be again 4, right? 4 variance of y plus variance of y. And then basically you need to take this minus 2 outside. Now there won't be any plus. So basically it will minus 4 covariance of x comma y. Okay. If both are equal, then definitely you can cancel out these terms. Then you are just remaining with something like 4 and 4 will get cancelled out. So you will be getting something like this, right? Covariance of x comma y equal to minus of covariance of x comma y, which means 2 you can say, which means 2 into covariance of x comma y equal to 0, which means covariance of x comma y equal to 0, right? Covariance of x comma y is 0. So can you say they are uncorrelated? Imply that covariance of x comma y is 0, hence they are uncorrelated, right? Okay. Now, there's a second question, which is saying that if variance of both are equal, then are they uncorrelated? No, actually, this doesn't tell you anything about the covariance of x comma y. So it may be 0, may not be 0. So uncorrelated means that covariance has to be 0. Okay. So this, if the variance of two is same, it doesn't mean that covariance is 0. Okay. Now let's just see this question. Can you just simplify this? Okay. You can just try simplifying this. Answer is on the next page, so you can just try. Okay. So these are the few questions we have already done about the true false. Tell me quickly, this is true or false? This is true. Actually, it doesn't matter if you're adding the constant. What about this? Yeah, this is also true. This one? Yes. So this is also true. This is also true, right? Which means x plus y comma z plus w. So here z plus w you just treat it as one random variable. Then you can write like this, right? Then you can write like this. What about this? This was also true, right? What about this? Okay, sorry, this is a new question. So let's just do it. So what they are saying, suppose x and y are are uniformly distributed between -1 by 2 to 1 by 2. Okay. And variance of x minus y is given to be 1. Okay. So by the way, from this, can you tell me the variance of x and variance of y? Do you remember variance of uniform random variable? I think it was b minus a whole square divided by 12, right? Do you remember? If if this x is uniformly distributed between A to B. Do you remember this from the module 1? That if x is uniformly distributed from between A to B, then the variance of x is coming out to be b minus a whole square divided by 12. So it will be, I think, 1 by 2 minus 1 by 2 whole square divided by 12, right? So which is basically, I think, 1 by 12, right? So this is the variance of x, and which is variance of y, which is 1 by 12. Okay. Now what they're asking, they are saying that variance of x minus y is also given to be as 1. So from here, can you say something? So they are saying that variance of x minus y is also given to be 1. So variance of x minus y is same as variance of x uh, plus, or maybe I can just write it, I mean, let me just write all the steps. So basically it is variance of x plus variance of minus y, and then plus 2 into 2 into covariance of x comma minus y, right? So which is same as variance of x plus variance of y plus, or you can take this minus outside, minus 2 into covariance of x comma y. So they're asking you this term, right? They're asking you this term, covariance of x comma y. And this is known to you, which is 1 by 12. This is 1 by 12. This is also given, right? This is given to be 1. So you can say 1 by 12 plus 1 by 12 is 1 by 6. 1 minus 1 by 6 is 5 by 6, right? So you can divide by 12. So I think it will be minus 5 by 12 or something like that. Yeah, minus 5 by 12, right? Okay. So I hope you can do this. That's not a tough question. I mean, this is easy question only. The only thing is that you need to know that what is the variance of x if x is uniformly distributed. Okay. See here, it is b minus a whole square divided by 12. Okay. Now let's just see this question, which I have taken from MIT. So what they are saying, suppose that x1, x2, x3 are uniform random variable from 0 to 1. Compute the variance of the first variable x1. So I think it is b minus a whole square by 12, right? So b minus a whole square by 12, it is just 1 by 12. Same as previous one, which is okay. Okay. Now what they are saying next, compute the covariance x1 plus x2, comma x2 plus x3. Okay, let's just do this. So x1, x2, x3 are basically uniform random variable here. Okay. Now they're asking you to compute this covariance. So what it will be? Now let's just do it step by step. Covariance of x1 plus x2, you can say, comma x2 plus covariance of x1 plus x2, comma x3. Now this is same as covariance of x1, comma x2 plus covariance of x2, comma x2 plus covariance of x1, comma x3 plus covariance of x2, comma x3, right? Okay. So basically this x1 will go with x2 also, with x3 also. Similarly, this x2 will go with x2 also, with x3 also. So basically these are the four terms. Now, I think this is same as the variance of x1. Do you remember? Covariance of the same variable, it is variance of x1. This is variance of x2, which is known to us, right? These two are known to us. Okay. Now, they're asking to find out the covariance of x1 plus x2, comma x2 plus x3. So basically, this is 1 by 12, this is 1 by 12. So how to find this quantity and this quantity? Sorry, this is x1, comma x2. Yeah. So this is not the variance of x1. This is the variance of x2. Okay. Yeah, that's all. So this is the variance of x2, which is 1 by 12. But what about these quantities? Yes. So they have given us that these are the random variables which are independent, right? So if they're independent, then covariance is actually zero. Yes. So it is zero, it is zero, it is zero. So finally, 1 by 12 is the answer. Okay. All of them are zero except this term. Great. So this question I have taken from MIT. I hope now you understood that how to find the covariance and these things, right? Now let's just do more examples. Let's just do little complicated example, and then you will be gaining the more confidence. So let's just do this question which I have taken from Berkeley. So what they are saying, let's just define two random variable u and v. Okay. Then find out the covariance between u and v. So which means they are saying find out the covariance of x plus y, comma x minus y. So it will be covariance of x, comma x, covariance of, basically you can say, by the way, the covariance between x, comma y is also, okay, just for the sake of notation I'm telling you, it is also written like this, sigma xy. Okay. So they're asking you to find out this covariance. Now what you can do? So you can say that this is nothing but, okay, sigma xx, or the variance of x, right? And then plus sigma, or maybe let me write it in the covariance form. So it is basically covariance of x, comma x plus covariance of x, comma minus y plus covariance of y, comma x plus covariance of y, comma minus y. Okay. So tell me, aren't these two terms equal? Right? So these two terms will get cancelled with each other, right? Because this is covariance of x, I mean, this is minus of covariance of x, comma y. This is covariance of x, comma y. So these two terms will get cancelled out with each other. So only covariance of x, comma x and covariance of y, comma minus y is remaining, right? And which is basically same as covariance of x, comma x minus covariance of y, comma y. Okay, let's just see that what they have in their final answer. Yeah, so variance of x minus variance of y. So basically it is a variance of x and it is a variance of y, right? So it is variance of x minus variance of y. Okay, they have used, the fundamental formula, which is also fine. and we have used the property, which is also fine. Okay, so they have used this particular formula, and then from the expectation they are calculating, then this is same as the variance, which is okay. Okay, now let's just do this question. This is related to some, let's suppose the PMF or PDF is given. So they are saying the joint density function. So it is the joint probability probability mass function. So basically they are representing it by F, but that's fine because this is a discrete random variable. So it is a joint PMF. You can say it is a joint PMF. Okay. So what is the covariance between X and Y? That's what they're asking. Let's just do this. So covariance between x comma y is basically nothing but expectation of xy minus expectation of x into expectation of y. Okay. So do you remember from this joint PMF how to find out the expectation of any function of random variable? So for example, if I want to find out expectation of xy, then it will be two summations, all the values of x, all the values of y, and then xy into the joint PMF, right? Similarly, what is the expectation of x? X plus 2y divided by 8. So what should I write here? Tell me if I need to find out the expectation of x. Yes, it will be just x, right? It will be the function that in which we are interested in. Okay. Now let's just find out these expectations and let's just calculate this question. So let's do this. Now what is the expectation of x? Let's just first find out the expectation of x. What is the expectation of x? It will be summation over all the possible values of x, all the possible values of y, right? Because it is a joint PMF, and then x into x plus 2y divided by 18. So x is varying from 1 to 2 and y is also varying from 1 to 2. So which means that you can say, uh, okay, so here it is okay. You can write anything first, but let me just write y first, okay? I mean y in the inner product. So it is y into x basically. Now, let me take this x outside. Okay, just because of that, I'm writing in this way. Let me take this x outside. So this is x into summation of y, x plus 2y divided by 18. Okay, so let's just do this. So this is summation over all the possible values of x into all the possible values of y. So if you take all the possible values of y, it is only 1 and 2. So if you take 1, it will be x plus 2 by 18. If you take 2, this is x plus 4 by 18, right? So it will be 2x plus 6. Uh, okay, so how much it will be? So 18 will be there. 2x plus 6 by 18, right? So it is 2x plus 6 by 18. So you can say it is nothing but all the possible value of x into 2x plus 6 by 18. Okay, now do you want to calculate this particular quantity? If you put 1, then it will be 1 into 2 plus 6 by 18. If you put 2, then it is 2 into 2 plus 6 by 18. So how much it is? It is basically 8 plus, this is 4 plus 6, 10, then 20 by 18, which is 28 by 18, right? Okay, 28 by 18 is the expectation of x. Let's just first check whether this expectation of x is correct or not. So it is correct, right? Okay, they have first found out the marginal marginal PMF. Okay, this is the PMF. They've just first found out the marginal PMF, and then using that, they are doing the expectation. Okay, you can do this way also, and you can directly substitute in this way. Is this fine to everyone that what we are doing here? Okay. If you want to find out the expectation of any function of random variable, you can just substitute it, okay, directly. Or maybe you can just find out from this joint, you can find out the marginal, okay, the way they are doing. How to find out the marginal? You can you just marginalize, which means you can, if this is the joint, then you can just marginalize first, okay. Actually, this is what we are even doing here. This is, you can say, the marginal PMF, okay. This is the marginal PMF. right? So anyway, you can do in both the ways. It doesn't matter in which way you are doing. Now, similarly, you can find out the expectation of y. How? You can put the double summation, or you can first calculate this inner summation, which is the marginal PMF, and then you can find out the expectation of y, which is coming out to be 29 by 18. Okay. So here it is 28 by 18, and this is 29 by 18. Now, expectation of x into y. How to find out the expectation of x into y? In the similar way. Okay. So let's just find out the expectation of x into y. So see, for all the possible values of x, for all the possible values of y, x into y like this. So if you open up, it will get open up like this, and then you just need to put all the values here, right? This is given. This is given. I mean, this function is given. So you can just plug in all the values. This is the answer you will be getting. And finally, the covariance will be xy minus x expectation of x into expectation of y. So if you calculate it, this is the quantity. This is which is coming out. Okay, cool. Now let's just solve more questions. Suppose they give you something like this, right? So here, from this observation, what they're saying, I mean, about x and y, what do you think? They're discrete or the continuous random variable? See, earlier also they have used, f notation. Okay. Sometimes some of the authors basically they just say density, but that's fine. Okay, it is actually joint mass function, you can say. Okay, joint probability mass function. But since it was very clear from this definition that it is discrete. Okay, because they are taking the discrete values. Now, from this, you can say it is continuous, because this is between 0 to 1. Okay, both the variables are between 0 to 1. So it is actually the continuous. Okay. Now you can use the similar formula, which is like this. So the covariance between x and y is equal to expectation of xy minus expectation of x into expectation of y. Okay. So expectation of x into expectation of y. So this is basically, you can say, uh, the covariance formula. Now, how to find out the expectation of xy? It is similar, like the previous case, but here we will be just using the integration 0 to 1, 0 to 1, xy, fxy, right? And how to find out the expectation of x? Again, the same thing, 0 to 1, 0 to 1, x into fxy. This is the expectation of x. How to find out the expectation of y? 0 to 1, 0 to 1, y into fxy, right? This is the expectation of y. So this is expectation of y. This is expectation of x. This is expectation of xy. Okay. So it will be just that this particular quantity will be keep on changing based on the function that you are using. Okay. Okay. Again, they have first found out the marginal PDF, and then they have used the marginal PDF to find out the expectation, which is also fine. I mean, you can do in this way, or you can directly double integrate. Okay. So if you calculate it, then you will get the answer, which is something like this. Okay. Is this fine? Okay. You just need to do the calculation. You can just try it once and can see if you're getting the same answer or not. Now, let's just see this. Okay. So again, I think this is a continuous random variable. So the conditions are given something like this. And then they're asking what is the covariance between x and y. Okay. So you can try it out. There's a solution on the next page. It is just that limit will be changing something. Okay. Based on the conditions, limit will be changing. So x can go from 0 to 1, but y is having the particular limit from 0 to 1 minus x. So whenever you are having the limit of y, it is just 1 minus x. But whenever you are having the limit of x, it can go to 1. Okay. So like this, you can find out this, and then you will be getting the answer. Okay. Now let's see this. If the product moment of x and y is 3. Okay, so moment basically is something like expectation only. Okay, so basically they are saying expectation of x into y is 3, and the mean of x and y are both equal to 2. Then what is the covariance of random variable, this and this, what is the covariance between these two random variable? So basically, moment actually, it is also, I mean, the expectation is also called as moment. Okay. So there is like, it is not in the gate DA syllabus, so that's why I'm not going much deeper into this, but it is called first moment. Okay. First moment. First moment of any random variable is expectation of x. Second moment is expectation of x square, and so on. Okay. So like if they are just saying moment, it means first moment, which means they're talking about the expectation. Okay. Now they're asking you the covariance between these two random variable. I think it is easy. Why? Because the expectation of x, expectation of y, both are given. Expectation of x into y is also given. And now you just need to simplify this. Okay. So for example, you can just simplify this particular expression, and then you can see what you're getting. So this is given as 3. These are given as 2. So the covariance between x and y is coming out to be -1. Okay. And then you can just simplify this expression. Okay. Now let's just see this question. So what they're saying, flip a fair coin 12 times. Okay. So this question I've taken from MIT open courseware. So they're saying that flip a fair coin 12 times. Let x be the number of heads in the first 7 flip and y be the number of heads in last 7 flip. Okay. So if you are flipping it 12 times, then x is the number of heads in the first 7 flip. So basically, it is like this. These are the, let's suppose, 7 flips. Okay. Um, or maybe let me write like this. Let's suppose these are the 5 flips. These are the 2 flips. And these are the again 5 flips. So x is number of heads here in the first 7 flips. Y is number of heads here in the last 7 flips. Now they're asking you to find out the covariance between x and y. Okay. Do you want to try this question? Okay, just try it for 1 minute and let me know if you are getting something. Okay, so what you can do now, you can say that this x is number of flips in first 7 flip, number of heads in first 7 flips, right? So you can break this x into the indicator variable or the Bernoulli random variable, which means you can say that let's suppose that this is x1. Okay, I mean number of heads in the first flip, number of heads in the second flip, and so on, right? Number of heads in the 12 flip is x12. So if you do this, then what is your x? Your x will come something like this. Okay. You can break this x into x1 plus x2 first 7 flips. So till x7. Similarly, you can break this y to x x6 plus x7 till x12. Okay. Now, if they ask you to find out the covariance between x and y, it is same as the covariance between x1 plus x2 till x7, comma x6 plus x7 till x12. See, in these kind of cases, okay, whenever you have these kind of form, in these kind of cases, most probably you will be getting covariance between most of the pair at 0. So see x1, so you can say xi and xj are independent here, right? So here you don't have any term of x1. So x1 comma anything will be anyway 0, right? Similarly, x2 comma anything will be anyway 0. So similarly, s6 here x6 comma x6 will be only survive. Similarly, x7 comma x7 will only survive, right? Because this is the only common thing. So in these kind of cases, whenever you have these kind of expression, then in these kind of cases mostly you will be getting most of the pair as 0. So what is the covariance between x6 and x6, which is the variance of x6, right? Plus variance of x7. So if it is, the binomial random variable, sorry, if it is the Bernoulli random variable, which means it can take the value only 0 and 1 with the probability, let's suppose P, then what is the variance? P into 1 minus P, right? So here, let's suppose it is a fair coin, then the variance is P into 1 minus P, 1 by 2 into 1 by 2, which is 1 by 4. Okay. So it is 1 by 4 plus 1 by 4. It is 1 by 2. Okay. It was easy, but nice question. Okay. Finally, it is 1 by 2. Now let's solve the similar question, but in fact the smaller one. Okay. Again, this question I have taken from MIT. So what they are saying? Flip a fair coin 3 times. Okay. Now they are just saying 3 times. Let's suppose 1, 2, 3. X with the number of heads in first two flips. So this is X with the number of heads in first two flips, and Y with the number of heads in the last two flips. This is Y. Okay. Then we need to compute the covariance. So it is just like this question. So by the way, why you think that between X and Y, if you are finding out the covariance between X and Y, then only it is depending on X, like the X6 and X7, which means the sixth flip and seventh flip, because these are the only two flips which are common, right? 6 and 7. Okay. So the covariance between X and Y actually doesn't depend, because these are independent, right? This is independent of this. So only this is the common thing. So that's why it was the variance of X plus variance of Y. Similarly, maybe you can directly say from here that what it will be if you directly apply the intuition. It will be variance of the middle term, right? Variance of X2, which is just 1 by 4. Okay. If you directly apply the intuition. Okay. 1 by 4 is the answer. Okay. You don't need to do all of this. You can directly say 1 by 4. Okay. Or maybe this is a little long method, I think, right? But if you really want to do it, then you can break it down into, X1, X2, X3, and then you can do it. But otherwise, from the past observation, we can say it is directly variance of X2. Okay. Variance of this middle one. Let's suppose if multiple are common, let's suppose if let's suppose 5 are common. Okay. Let's suppose x3 to x8 is common, then it is variance of x3 plus variance of x4 plus variance of x5, like this, right? Till x8. Okay. Now let's solve this question. What they are saying, suppose that we flip a fair coin 20 times. Let x be the number of heads in first 15 flips and y be the number of heads in last 10 flips. Okay. Then they are asking you to compute these quantities. Okay, just take some time and solve this question. Let me know what is the answer you are getting, at least for this. What is the covariance you are getting? Okay, let me know. So, what are the common things? You can say that it is first 15 and last 10, right? So in the first 15, let me just break it in 5, 5, 5, 5. This is X and Y is last 10, right? This is Y. So you can say the only 5 is common. So which means variance of 5 into variance of something, right? So 5 into variance of the xi. So it is 5 by 4. Yeah. So 5 by 4 should be the answer. So let's just check it. Yes, 5 by 4 is the answer, right? Okay. And now they're asking you to find out the expectation of x, expectation of y. So what is the expectation of x? It is the expectation of it is basically very easy. Expectation of x1 plus x2 till x15. So what is the expectation of a single random variable? Yeah, it is basically p, which is 1 by 2. So if it is n random variables, then it is basically, you can say, 15 into 1 by 2, right? Which is np. Okay. Or maybe 15 into 1 by 2. This is 10 into 1 by sorry, x is basically number of heads. Yeah, this is 10 into 1 by 2. And what is the variance of x? What is the formula here? You can directly apply formula for Bernoulli. So I think it is np into 1 minus p, right? Okay. So the variance of x, variance of y, like this you can find out, okay? And expectation and variance of z also you can find out, right? Okay. Yeah. So they have also breaked it down into 15 and 10, and then they are doing the calculation, okay? Now, basically, if the expectation is zero, let's suppose expectation of x1 is zero, expectation of x2 is zero. If the expectation is, is zero, in that case, the covariance will be just this product, right? I mean, this is just simple observation, okay, that you can do. Now, let's just move to a next topic, which is covariance matrix. This here we will just introduce this topic, but we will be using this covariance matrix later on in the machine learning. So that's why I thought that you can have the little glimpse of this covariance matrix here. Okay, we will be using that in the, can anyone tell me the topic name, where it is majorly used in machine learning? PCA, okay, principal component analysis, right? So let's just see what is this covariance matrix. It says that, let's suppose these are the two random variables, okay? Let's suppose there are or maybe any number of random variables, doesn't really matter. Let's suppose there are three random variables, a, b, and c. You write those three random variables like this, okay, in the column and in the row. Then basically this particular quantity is covariance of a comma a. This particular quantity you need to write covariance of a comma b. This is covariance of a comma c, and so on. This will be, can anyone tell me what will this quantity? This will be covariance of c comma b or b comma c, right? Okay. So basically, if you find out the covariance between every two possible pair and represent in a matrix, then it is called covariance matrix, right? So covariance between every two possible pairs. Okay. And this covariance is nothing but variance of A. I mean, on the diagonal, you will be having variance of A, variance of A like this. So basically, you can represent covariance with the sigma also, as I told you. So it is sigma of x comma x, x comma x, x comma y. If this is x, this is y, then you can write like this, right? And this is same as variance of x, and then covariance of x comma y. Then this is covariance of x, y, and then variance of y. Okay. Is the definition clear that what we are doing in this matrix? Some people call it variance covariance matrix. Okay, variance and covariance matrix. Some people directly call it covariance matrix. So basically, what it encode, it basically have the covariance between every two possible pair. Okay, so it is nothing but covariance between every two possible pairs. Okay, why that is useful? You will get to know. Okay, today only you will get to know that how it is useful, and then in PCA we will be actually using it. Okay. Basically, PCA is highly dependent on the covariance matrix. We will be using this in the PCA, which is a machine learning topic. Okay. So, for example, if there are n random variables, then for the n dimension, you can write like this. Okay, x1, x1, x2, x1 like this. Okay. For the n random variables, you can write like this. Tell me, is this matrix symmetric? So, can I say, if I just ask you true false, covariance matrix is symmetric? What do you think? Yes, right? So the answer is true. Why? Because because see here, let's suppose this is the diagonal. See here, if this is, let's suppose, x2. Okay, let's suppose this is x2. This is maybe let's suppose x1, x2, and let's suppose this is x3. Okay, so whatever you're writing, okay, x2, x3 here. Okay, whatever you are writing for x2, x3, basically the same thing you will be writing for x3, x2. Okay, which means, I mean, these two values are actually same. Why? Because the covariance is symmetric, which means covariance between covariance covariance between x2 and x3 is same as the covariance between x3 and x2. So for example, if you take this, right, so this is a diagonal anyway. Now this covariance, which is x2, x1, and x1, x2 is actually same. See here, xn x1 and x1, xn is actually same. So that's why it is symmetric. Okay, this is a symmetric matrix, and on the diagonal you are having the variance. Okay, on the diagonal you are having the variance. Okay, let's just see this question. What they are saying. Let Z1, Z2, Z3 be the uncorrelated random variables, each having the variance 1, and set x1 like this, x2 like this, and x3 like this. Determine variance covariance matrix of x1, x2, x3. Okay. So Z1, Z2, Z3, they are saying that they are having the covariances, the variance as 1. Now, they're asking you to calculate the covariance matrix. So let's just calculate. For the covariance matrix, I think we need covariance between every two pair. So let's just calculate covariance between x1 and x1 first. What it will be? Covariance of x1, which is same as covariance of z1, which is same as 1. I mean, it is given. Sorry, which is same as, this is variance, okay, not covariance. X1 and z1 is same. So that's why I'm just substituting it directly. Okay. X1 and z1 is same. Is this okay? Now let's just find out the covariance between x1 and x2. What it will be? So it is covariance of x1 is actually z1, x2 is x1 plus z2. So which means, let me write in the terms of z1 plus z2 basically, right? So what it will be? These are the uncorrelated random variables. Tell me. Yeah, it will be just a variance of z1. Why? Because the other term will be 0, because these are uncorrelated. So this is 1. Now similarly x1 and x3. So z1 and then x2 is basically z1 plus z2, and it will be z1 plus z2 plus z3. Okay. So z1 with z1 plus z2 plus z3. I think again it will be just, if you want to find out covariance between x1 and x3, again it will be just 1. Is this okay? Because it will be z1 comma z1 plus z2 plus z3, right? So let me write it, which is again 1. Okay. So x1 is done. X1 with x1, x1 with x2, x1 and x3 is done, right? Now, what else is remaining? I think covariance between x2 and x3 is only remaining, right? Okay. So what is the covariance between x2 and x3? X2 is z1 plus z2. X3 is z1 plus z2 plus z3. So here z1 will survive, z2 will survive. So how much it will be? Tell me the final answer. Yeah, it will be 2, right? Okay. So I think we have the answer now. So let's just check it. let's just make the matrix, I think. So the matrix will look like this. Variance of x2. Uh, okay, okay, yeah. So x2 with x2 is remaining, yeah. Covariance of x2, x2, right? It is a variance of x2, which is basically variance of z1 plus z2, right? So variance of z1 plus z2. So it is nothing but variance of z1 plus variance of z2, which is again 2. Okay. So I think these are the three random variables. So here x1, x2, x3. Here x1, x2, x3. x1 with x1, this is 1. x1 with x2. Okay. Or maybe let me write x2 with x2. x2 with x2 is 2. x3 with x3. Yeah, x3 with x3 is also remaining. So it is z1 plus z2 plus z3. And z1 plus z2 plus z3. Covariance between z1 plus z2 plus z3. And covariance between z1 plus z2 plus z3, right? So how much it will be? I think z1, I think it will be 3, right? See, covariance of z1 plus z2 plus z3 with z1 plus z2 plus z3. So I think this z1 will survive, z2 will survive, z3 will survive. So that's why it is 3. Sorry, that's why it is 3. Now, let's just find out these terms. 1, 2, 3 terms are remaining. So x1, x2, I think we know this is 1. x1, x3, I think that's also known. This is also 1. x2, x3, this is 2, right? Okay. Anyway, this is symmetric, so I'm not writing these values. So 1, 1, 1, 2, 2, and 3. Yeah, 1, 1, 1, 2, 2, and 3. Okay. If I just omit these values, then this is the answer. Okay. So now can you find out the covariance matrix? Tell me. Let's just see one more example. Let's see if you can find out. Okay. Suppose they're asking you to find out the covariance matrix of this y1, y2, y3. Okay. Just try it out. Okay, so you need to find the covariance matrix. So first you can find out the variance of each of them individually, and then you can find out the covariance between every pair. Okay, so just try it out. Okay, it's not very tough question. It's approachable question only. So you can just try it later on as an homework, and answer is already on the next page. Okay, so answer is there. You can just try it out. Right? It's a good practice question. Now, let's just see the geometric interpretation. Okay, you can say the geometric interpretation or the meaning of covariance matrix. Okay, or you can say the geometric meaning. So, let me write it. Yeah. So, suppose that this is the covariance matrix which is given, right? Then what does this mean? Or maybe, see, this is the data. Okay, this is the data. And if we find out the covariance matrix between these features, okay, let's suppose this is x1, x2, or x and y. Okay, this is the covariance matrix of x and y, which means that you have xy here, xy here. Okay, so this is the covariance matrix between these two features. Now, what do you think here? That this particular spread is telling you what? This means that you have good enough spread. Okay, if you just project it on the x, then you will say that you have good enough spread on x, you have good enough spread on y. Okay, which means the variance of x and the variance of y is good enough. Variance of x and variance of y, these are the variance of x and y. This is the covariance. Covariance will tell you that, see here, are these positively correlated, which means can you at least say that if x is increasing then y is increasing? Yes, right. So that's why this is a positive number. Okay, this is a positive number. Why? Because because if x increasing, then y increasing, and that's why the covariance is positive. Okay, this number is telling you this is positive. It is telling you that if x and y, x and y both are increasing at the same time, this number is telling you what? The spread, you can say this is telling you spread along x, this is telling you spread along y, and this is anyway symmetric, so this 4 and this 4 is actually same. So this is telling you spread along y. Okay, so 6 means that spread along y may be little higher. Okay, maybe little higher than spread along x. Okay, maybe. I mean, I'm just telling you the intuitive meanings. So let's just see the next example. So in this example, this 5 and 6 are same because maybe the spread along the x is 5, spread along the y is 5, y is 6. Okay, these are the variance of x, and this is variance of y. But this is minus 4. Minus 4 is telling you that covariance between x and y is negative, right? So covariance between x and y is negative, which is minus 4, which means it is negatively correlated, which means if x is increasing, then y is decreasing. Okay. So basically, this is the data. Okay. This is the data. This is the plot of data. And this is the covariance matrix. Okay. So basically, the covariance matrix tells you the shape of the data, or maybe the vice versa. The shape of the data can tell you the covariance matrix. For example, if this is the covariance, this is the data, then you can say that okay, spread along the y is actually very low, right? So that's why this number is very low. Spread along the x is quite high, so that's why this number is quite high. And you can say that if x is increasing, okay, if x is increasing, then y may increase, decrease. Actually, there is not much correlation. So this number is captured by this. Okay, are you getting the point? So basically, you can say that data plot can tell you what the covariance matrix going to be, and vice versa also. Okay, if covariance matrix is given, then little bit you can get the idea of the about the data plot, which means if let's suppose only this is given. Okay, for example, let's suppose they don't give you what is the actual data. Okay, what is the actual data? Suppose they don't give you at all, then can you infer? Maybe you can say that okay, this is 0 means they are not correlated. Maybe something like this. Okay, the equal, they are not correlated, but x is having the higher spread, so let's just have higher spread on x, but y is having the lower spread, so maybe something like this, right? Y is having the lower spread. Okay, this is lower spread, this is higher spread. Is this okay? For example, this here, they're not correlated. X is having the lower spread, Y is having the higher spread, isn't it? For example, okay, this is the question. So what they're saying that what might be the scatter plot? Scatter plot means you can assume like this means basically the data plot. Okay, scatter means the points. Okay, scatter means the point plot basically for the given covariance matrix look like. Okay, this is actually a question. Okay, which I have taken from this university. Okay, the as it is question is given there. I have just taken the screenshot. So which means they are saying, given this covariance matrix, can you tell me what the graph might look like? Okay. So see here, they are saying that this is basically the spread along the x is high, spread along the y is low. Okay. So you can say spread along y is low. And this one means positive correlation or negative correlation. It means co positively correlated, right? which means it might look something like this. Positively correlated means something like this. Okay, maybe increasing, like slope is positive basically, and spread along y is low compared to x. So maybe something like this. Okay, which means if you see the spread along the y, it is little low compared to spread along the x, right? Something like this. Are you convinced? It might look something like this, which means like this. Tell me. Right? So covariance matrix is very good thing to tell you that how the data might look like, and similarly the vice versa. Given the data, you can assume. You can infer the covariance matrix. Given the covariance matrix, you can infer about the data. Okay. So for example, this is the answer. Okay. See here, the spread along x they have given good enough. Spread along y they have given little. Okay. So this is what you can say spread along y. This is spread along x. Okay. Understood now? So basically, given the covariance matrix, you can infer about the data, how the data is actually looking. So for this region, actually the covariance matrix is very important. Okay, you will get to understand why in the PCA. But here, let's just see little bit more about the geometric interpretation of the covariance matrix. For example, if let's suppose this is the data and this is the covariance matrix, okay, which means 5 and 1. 5 means spread along x is good enough. Spread along y is little less, which is fine. I mean, this is okay. And 0 0 means that it is basically not correlated, okay, which is like this. Okay, now if you see this covariance matrix, then can you tell me the eigenvectors here? See, if you multiply by the, let's suppose 0 1 and 1 0, if you multiply with 1 0, then what you're going to get? 5 and 0, right? Isn't 1 0 is the eigenvector? 5 into 1 0, right? Similarly, isn't 0 1 is the eigenvector? If you multiply 0 1, okay, if you multiply 0 1, then what you're going to get? You're going to get 0 1 only with the one eigenvalue. Okay. So 0 1 is the eigenvector here, and 5 0 is also eigenvector, basically, right? This is also eigenvector. Is this okay to everyone? So basically, sorry, not 50, 10. Okay. 1 0 is also eigenvector. So it is 0 1. Okay. 0 1 means this particular vector, right? I mean, this is actually this is 0. Okay. These are the negative points. So 0 1 means this particular vector. 1 0 means this particular vector. Okay. These are the eigenvectors. And let's suppose I also write the eigenvectors with this eigenvalue, which means if it is having the 5 eigenvalue, then I'm basically drawing 5 0. I'm drawing it long enough. I'm drawing it little short because the eigenvalue is lesser. Okay, which means basically what I'm saying, that if I know the eigenvectors, okay, let's suppose the eigenvector I know. This is the first eigenvector. This is the second eigenvector. Then using the eigenvector also I can say, or maybe using the eigenvalue, I can say that in this direction the spread is more, in this direction the spread is less. Okay, see, in the first direction, isn't the spread longer, which is the direction of the eigenvector v1, and v1 have the eigenvalue 5, that's why the spread is longer. Okay, so basically we will see in the PCA that these eigenvalues of the covariance matrix is extremely important. Okay, PCA just based on the eigenvalues of the covariance matrix, just based on this concept that the higher the eigenvalue, the more the spread. Okay, so you can say the higher eigenvalue will tell you the more spread in that direction. Okay, higher eigenvalue of covariance matrix. Okay, I mean of the vector, the covariance matrix basically. Anyway, you got the point, right? Higher the eigenvalue means that longer the spread in that particular, longer the spread in that particular eigenvector direction. Okay. And in fact, in PCA, we will prove that that this actually happens. Mathematically, we will prove it in PCA. Okay, that the highest eigenvalue or will tell you the spread. Okay, or maybe you can say that the eigenvector eigenvector associated with the highest eigenvalue will tell you the spread of the um, or maybe you can say the direction of the highest spread or the longest spread. So for example, let's suppose if this data is given to you, okay, let's suppose this data is given to you. I ask you that in which direction you are having the longest spread. So for example, let's suppose this data is given to you. Okay. I ask you in which direction you have the longest spread. Then what will you say? Will you say this direction or will you say this direction? Exactly this direction. You will say this direction. Okay. So basically, we will prove in the PCA that if you find out the eigenvector of this covariance matrix, okay, if you find out the eigenvector of this covariance matrix, then one of the eigenvector will be this, another eigenvector will be this. Okay. See, it is a real symmetric matrix, right? It is a real matrix and symmetric matrix also. So eigenvector corresponding to different eigenvalues will be orthogonal. So eigenvectors here are the orthogonal. So one of the eigenvector will be this, another eigenvector will be this. And along this direction, the spread is highest. And along this direction, the spread is lowest or something like this, right? So basically, the eigenvector will tell you that the spread is how much, okay? So which means if I want to find out the direction in which the highest spread is there, I can take the eigenvector corresponding to the highest eigenvalue. Okay, so what I'm saying here is that if you we will prove it actually in PCA, but I'm just saying here it, okay, one statement. If you want to find out direction in which highest spread lies, then take the eigenvector corresponding to highest eigenvalue. Okay, and again we will prove this in PCA. Actually, PCA is just this. Okay, this is the whole PCA. Just the proof is remaining. You can say something like this. Okay. Okay. So let's see more examples. See here that this is the let's suppose this is the covariance matrix. This is the eigenvector. In this eigenvector, okay, the eigenvalue is let's suppose 5. So in this direction, the spread is highest. Okay. For example, let's see more examples. So suppose that this is the covariance matrix. Let's suppose these are the two eigenvectors. Okay. Here the eigenvalue is 5. Here the eigenvalue is 1. Okay, so here this is not the diagonal matrix. See, earlier I have taken the easy examples. It was a diagonal covariance. It was also the diagonal. Okay, it was also the diagonal. So it is. I mean, in case of diagonal, the eigenvectors are 1, 0 or 0, 1. But if it is not diagonal, then eigenvectors could be anything. Okay, so if these are the two eigenvectors, then this is the eigenvector or this is the direction in which the highest spread is there, right? So in this direction, we have highest spread. Okay. Similarly, in this direction, we have the highest spread. Why? Because the eigenvector in this direction have the highest eigenvalue. Okay, understood? So why you think this information might be useful? That in which direction you have the highest spread? Why you think this information might be useful? Yes. So what we will be doing, let's suppose these are the two dimensions. I don't want to work with the two dimension. We will see in the PCA. Then I will just use one of this direction. I will say, okay, let me, instead of using this X and Y as two dimension, two features, let me just use this direction. I will project all the points on this particular vector. You know how to project, right? So we will see again in the PCA that how to project. So we will be projecting all the points on this direction, and then we will say that let's just use only this direction. Let's not use other direction. Why? Because I want to reduce the dimension. Okay, I don't want to work with the multiple dimension. Let's suppose just want to work with the few dimensions. Okay, that's where it will be very useful, and we will see this practically also. Okay, which means that it is not much harm, in the sense that if you even just use one of the direction, then it is not much harm. Okay, which means that it is also representing the data almost accurately. I mean, obviously there is a loss of precision, but not much. We will see that in the PCA. But here I just want to convey the meaning of the covariance matrix. Okay, don't get afraid. Just see that if the covariance matrix is given, then at least you can infer about the data, how the data will look like, and vice versa, right? Like this, right? This is the first interpretation. Second thing I just want to convey that if you find the eigenvectors of the covariance matrix, then the direction of the highest the eigenvector direction corresponding to the highest eigenvalue having the highest spread. That is something we will prove in the PCA. Is this okay? Or if that is not getting that is not much understood to you, then this is fine, because we have not proved anything. It was just an idea. But one thing should be clear, that given the covariance matrix, you should be able to infer the data, that how the data might look like. Or given the data, you might be able to see that, okay, what are the numbers, maybe it is positive like this. Okay, so this should be okay. This eigenvalue, the highest spread, this is okay if you don't get it. But the other part should be okay, that given the covariance matrix, at least you should be inferring that, okay, how the data might look like. Okay, is this fine? The eigenvalue, eigenvectors, forget. But if you just solve this question, okay, if you just solve this question, that how the data might look like, then the purpose is solved. Okay, it was just a bonus thing, I can say. Okay, just something extra that I just conveyed here, which was not actually necessary, but I just conveyed it for the sake of information. But we will do it again in the PCA. Okay. Now, regarding the covariance, let me just tell you one thing. Let's suppose you have this data, okay, which is X and Y. If you find out the covariance here, then it is 16.5. Now, what do you do? Let's suppose you divide this X by 10 and you divide this Y also by 10, which means you just scale it, right? You just scale it. Then in that case, the covariance will be changing, right? Covariance will be changing. So, uh, now let's suppose the covariance is coming out to be 0.2. See, here the covariance is 16.5, and let's suppose here the covariance is 0.2, which means that what I'm saying here is that the data is same, right? Data is same. Okay, it is just a scale, which means, for example, see the covariance, you are basically having the matrix of the covariance. Yeah, this is 0.165, which approximately it is, they might have written as 2. Okay. Yeah, you need to divide by 100, then it will be 0.165. That's fine. So basically the covariance is meaningless, in the sense that it is unit square. Okay. You can say it is expectation of X, which is unit into expectation of Y, right? So, so for example, let's suppose this is, X is, let's suppose, some kilometers. Okay, this is also kilometer or something like that, right? This is kilometer square, which doesn't make much sense. Or for example, let's suppose X is kilometer and Y is maybe anything. Okay, maybe let's suppose the number of kilometers you run, this is calorie one. Okay, calorie, something like this. This will be the variance will be something in the terms of calorie into kilometers, something like this. So basically the unit of this variance is actually meaningless. And it might so happen that instead of kilometer you might be measuring, or instead of kilometer you might be measuring into the meters, or maybe instead of meters, let's suppose here it is meters, you might be measuring in the kilometers. So if you're just changing the scale, okay, from meter to kilometer like this, then data is not changing, but the covariance is changing. Okay. So if you're changing the scale, then data doesn't change. Okay. Instead of meter, if let's suppose you are measuring in the kilometer, then data is same. Okay. You're just changing the scale. But the covariance is basically sensitive to the scale. Is this fine to everyone? What I'm trying to say? Right? So covariance is very much sensitive to the scale. Why I told you this? Because you will get to understand one thing from here, which means based on the scale, the covariance might be changing, right? Actually, not might, it will change, right? I mean, until and unless you adjust like this into 10 and then you here you buy into 10 and here you do X by 10, then it will not change. But in most of the cases, it will change. Okay. So, so it is very much sensitive to the scale, which means if I say that covariance is 16.5, then does this tell you anything that, okay, they are highly correlated? Or if it is 0.2, very less, does this convey anything? See, the 16.5 is telling you that, okay, data is like this, and 0.2 is also telling you the data is like this. So, what I'm trying to say here is that the value of the covariance doesn't convey anything. 16.5 also says the data is like this, and 0.2 also says the data is like this, isn't it? So, the value of the covariance is not a matter of important. The only the sign of covariance is important, which means 16.5 is also saying that this is the data, for example. Okay. And 0.2 is also saying this is the data. Just a scale is different. So the covariance value doesn't tell you anything. Only the sign matters. Okay. So covariance value doesn't tell anything. Only sign matters. Is this understood? So which means you can measure it in any scale. Okay, doesn't matter. Covariance could be very less, very large, depending on the scale. Okay, depending whether you are having big values, for example, 1,000, 5,000, like this. Covariance could be very large. Covariance could be very low also, depending on just a scale. It is not normalized. Okay, normalized in the sense like it is not divided by something. It is not normalized. It is just a value which depends on your scale. So here the sign tells you things, but the value doesn't tell you anything. So this is very important. Okay. So that is why what they have done, they have actually introduced something called as correlation. Okay. So they have introduced something called as correlation, which is also very small topic. But we will do this in the next class. It is just like that they're making this is normalized. Okay. So they're dividing the covariance with something so that it is normalized. So we will see this correlation in the next class. Okay. But I hope the motivation of the correlation is clear and the covariance is completed here. Okay. So I will upload these slides and you can just revise this topic and then we will start in correlation. Okay. Thank you, everyone.